In today's lecture, we will discuss parallel processing, pipelining, and arithmetic pipelining. So first of all, what is meaning of parallel processing? So parallel processing is a term which denotes techniques which requires simultaneous data processing task. Now the advantage of parallel processing system is computational speed of the system. So it increases computational speed of the system, as well as it provides higher throughput. What is meaning of throughput? It is the amount of processing or amount of tasks which are completed per unit time. Now, the system may require, let's say, it may have two or more ALUs to execute more instructions, or the system may also have multiple processors which are operating concurrently, and it will also provide speed up to our system. But in case of parallel processing, the amount of hardware also, as it increases, so cost will also increase. So on the basic level, if we consider the systems, if we talk about registers which are used for storing data, so either we can have shift registers which are storing our data in serial fashion, one bit at a time, or we may also have registers with parallel load capabilities which stores all the bits in a word in parallel fashion. Now, another type of parallel systems may also have multiple functional units. As you can see in this diagram, we have different functional units for arithmetic, logic, and shift operations. Further, we can also have different types, let's say integer and floating type of adder subtractor, and floating point multiply, floating point division. So separately, these systems can also be there. Now, for computer architectural classification, M.J. Flyen has considered the classification based on number of instructions and data items which are manipulated simultaneously. So, if we consider the normal operation of a computer system, it's to fetch the instruction from memory and execute them in the processor. Now, there are two more terms, let's say instruction stream. So what is instruction stream? The sequence of instructions which are read from memory is called as instruction stream, wherein the operations performed on the data in the processor, it constitutes a data stream. Now based on these two, how they are manipulated, Flyen has shown four types of classification. One of the classification is SISD, which is single instruction stream and single data stream. In single instruction, single data stream based systems, computer will have a control unit, a processing unit, and a memory unit. As you can see in this diagram, we have control unit, processing unit, and memory unit. In this system, sequential operations are obviously possible, wherein we can also have parallel processing. How it can achieve parallel processing? Either through multiple functional units or by pipelining processing, which this pipelining processing concept we are going to see in detail. So in this SISD based system, von Neumann architectures basically comes under this category. Then the next category is SIMD, which is organization that includes multiple processing units, but these processing units are under the control of a single control unit. So that common control unit monitors all the processing units, and we also have shared memory. As you can see from this diagram, this shared memory is used to communicate between different processors. So in SIMD based system, if we say, let's say if we have array based processors or vector based processes, so these kind of systems comes under SIMD category. Then the next is MISD. MISD is multiple instruction single data stream. So this concept was just developed as theoretical concept. There was no practical system developed on this concept. Then the last concept is MIMD, which is multiple instruction and multiple data stream. So if we consider multiprocessor system which has capability of executing several programs at the same time, so they come under this category. As you can see in this diagram also, again we will have shared memory, we will have multiple processing units, but we too have multiple control units. So this was the classification which was provided by Flynn. And first of all, we are going to consider pipelining based system. So what is meaning of pipelining? Pipelining is a technique which decomposes a sequential process into sub operations. That means whatever process given to us, first of all, it will be divided into sub operations, and each sub process or sub operation will be executed in a segment. So special dedicated segment will be there concurrently with all other segments. Means how we can visualize a pipelining based system. It will have collection of segments, and each segment will perform some partial processing task, and those tasks, whenever one task completes from one segment, it will be passed to the next segment in pipelining, and the final result will be obtained after the data has been passed through all the segments. Now, what is the advantage of pipelining and what is the difference between serial and this pipelining based system? So let's say, as I told you, we divide our task or process into multiple sub operations, and we will have multiple segments. So if we consider sequential operations, then all the subtasks, or let us call them tasks only, so all those tasks will be passed through each segment one by one. That means first task will be passed, it will complete, then second task will be passed, then it will complete. So that way, that is our serial operation. But what will happen in pipeline based system? When one task has completed one segment, when that is it is in the second segment, then in overlap fashion, second task can execute in the first segment. Similarly, it is the case for the other. Like if the first task was there in, let's say we have three segments, so if it is in third segment, so second task can be there in the second segment, and as well as next task can be there in the first segment. So these three operations, whatever operations in those subtasks, that can be operated in simultaneous manner. So we will also see example based on this pipelining processing. Let us see, we want to perform AI into BI plus CI, which is for I from 1 to 7. So first of all, for any pipelining based system, we have to decide on what are segments, what all segments are there in this system. So we can divide this task into three sub operations. Okay, so we will have three segments in our pipelining. What are those three segments? First of all, input AI BI into R1 and R2, then perform R1 into R2 and store in R3, and CI, which is stored in R4, and the last segment is perform addition of R3 R4 and store result into R5. Now, these three segments, we will first of all see how we can execute in the pipelining, as well as we will also see what kind of system in this pipelining will have. So see, in this case, as I told you, in pipelining based system, first of all we will require segments. So this is our first segment, this is our second segment, this is our third segment. So AI BI will be stored in R1 R2, then multiplication, and we can have CI stored into R4, and then R3 and R4 will be added. But can we see overlapping over here? No, we can't see, because right now we have just shown it for generalized I. But now we will see in this diagram, we will see how we can execute it for I1 to 7, and that too in overlap fashion. And that is our ultimate goal. We don't want these tasks to execute in serial fashion. We want these tasks to execute in pipeline manner. So as we have initially decided how many segments we are going to have, three segments. So you can see segment 1, segment 2 and segment 3. Now we will also see in how many clock cycles this whole task will get complete. So first subtask, or let's call this as task only. So this first task was to store A1 and B1 into R1 R2. So it will be performed in first clock cycle. Then in second clock cycle, A2 and B2 will be stored. But what we can do with A1 B1? parallelly, or let us call it in overlap manner, which operations will be performed. So a1 into b1 we can perform, and result is stored in r3, and we can also store c1 into r4. Now in third clock cycle, what we are going to do, a3 b3 will be stored, as well as a2 into b2, and c2 will be stored in r4, as well as now we can perform a1 into b1 plus c1, and in R5 we can have our result. So similarly this is repeated. So this will be repeated up to 7, like A7 B7 we have got. Now after this, in the next clock cycle we will have A7 into B7 and C7 will be stored, and in the next, after that clock cycle, we will have A7 into B7 plus C7. So see, rather than executing sequentially, if we execute in this manner, then we can have overlap fashion in one go. Now, considering this general pipelining system, what are the general considerations? First of all, our goal was to divide our operations into sub-operations. Okay, so these operations should be implemented by pipelining processor. Then we want some efficient system that need to repeat the same task many times with different sets of data. So if we consider a 4-segment pipelining, let us say, so what can be general structure? As you can see in this figure 9.3, general structure of 4-segment pipelining can be this one, wherein 4 segments are there, and as you know that after computation from every segment, we need to store or register or result into registers. So all the information which is flowing from adjacent states, it is the control of under common clock, which are applied to all the registers simultaneously. Now we define a task as a total number of operations performed going through all the segments in the pipelining. So this is the general architecture, wherein we have segments and we have registers in between each segment. Then we can also represent the behavior of a pipelining system using space-time diagram, as you can see in this space-time diagram. So like this is providing you access in terms of segments and clock cycles, means this diagram is segment versus clock cycle. Now what you need to show in this diagram, in horizontal axis, as you can see, there are clock cycle, and in the vertical axis there are segment numbers. So we are assuming here we have 4 segments in the pipelining, and in this we have, let's assume, 6 tasks which are from T1 to T6. So first of all, the first task will T1 task will be executed in the first segment. After the first clock, segment 2 is busy with T1 task, while as we know in pipelining we wanted to have overlapped operations. So T2 task can be performed in overlap fashion for segment 1. So segment 1 will be busy with T2 task. So same, the first task T1 is completed after the 4th clock cycle, right? And from then the pipe will start filling for a task at every clock cycle, means we have got our first result of first task at T1. For T1 task we have got in this 4th clock cycle. Afterwards the pipe will start filling for the next few tasks in the next cycles, that is in the 5th cycle T2 will complete, in 6th cycle T3 will complete, in 7th T4, in 8th T5, and then in 9th T6, right? So this is the general pipelining system. Now if we consider in generalized way, if we have, let's say, k segment pipelining with a clock cycle time TP, which is used to execute n task. First task T1 requires a time equal to KTP to complete its operation. Why? because as we have seen, it was passed through all the segments. So since there are k segments in the pipe, what about n minus 1 task? So as we have seen, once the first task completes, afterwards they next whatever task starts completing one task per clock cycle. So they will be completed in n minus 1 TP. So in every clock cycle, we will get one more task complete, right? So if we want to find out to complete n task with k segment pipelining, how many clock cycles will be required? So first task will complete in k, then we will have all the remaining tasks completing in the every clock cycle, every next clock cycle. So we can represent pipelining, the clock cycles required for pipelining system is k plus n minus 1. If we take previous example, how many clock cycles are required? 9 clock cycles. So how many segments we have? We have 4 segments, so k is 4. What is n? N is 6. So we can say that 4 plus 6 minus 1, which is 9 clock cycles, are required for pipelining based system. Now what about non-pipelining? If we perform the operation in non-pipelining system, then and if let us say that Tn is the time which is required to complete operation or task, then what is the total time which is required for n task? It will be ntn. Now the next thing which we need to find out is speed up S. Speed up S means if we implement pipelining in our system, how much speed up in execution time will be there for our system. So this we can find out that without using pipelining means non-pipelining divided by execution time for pipelining system. So this we can find out with ntn divided by k plus n minus 1 tp. Now as you know that n is number of the task, tn is the time to complete each task in non-pipelining system, tp means clock cycle time for pipelining, and k is the segment. So we have 4 segments, we have 6 tasks. Okay, now in this formula, if n achieves infinite means n becomes greater, very much larger than k, then we can say that we can have speed up as Tn divided by Tp, because n is much larger than k. So in this k plus n minus 1 will become n. So we will have Tn by Tp. Now another case is if we assume that time it takes to process a task is same in the pipelining and non-pipelining. That is, we will have Tn equal to KTP. So what is the speed up? Speed up will become S equal to Tn divided by Tp, and as we know, so after this we are assuming, as we know that Tn is what? KTP, because we have assumed this thing. So KTP divided by Tp is equal to K. It means speed up will be equal to your segment count, means number of segments, and the processing speed will be improved. So this was pipelining. Speed up means how much speed up we are getting if we are using pipelining. So the formula is, you need to find out the time for non-pipelining divided by pipelining, and then we have considered special cases wherein we have n very much greater than k. Okay, then what is speed up? And if Tn equal to KTP, then what is the speed up? Now let us consider arithmetic pipelining. So arithmetic pipelining is basically used for high speed computers. In this arithmetic pipelining, We will try to implement floating point operations. Okay, so here this arithmetic pipelining example. Okay, in any pipelining we have to divide our task into sub operations, right? So first of all, let us see if we want to perform floating point addition pipelining between two normalized binary numbers. So in general, let's say they are represented like this manner: x equal to a into 2 to the power a, and equal to b into 2 to the power b. So a and b are two fractions that are mantissas, and small a and b are exponents. Now, to perform floating point addition and subtraction task, we can have four segments. So what are those four segments? Now, first segment is compare the exponents. Second segment is align mantissas. Third is add. Let's consider it for add only right now. So add mantissas, and then the last one is normalize mantissas, or normalize whatever is the result after addition. Now, the first task is comparing the exponents. So let us see this example for x equal to this value and y equal to this value. Now, the first task was to compare the exponents. So how we can compare? By subtraction operation. So let us subtract these two exponents. 3 minus 2 is 1. Now, if these two exponents are not equal, means larger exponent 3 is chosen as the exponent of the result. So, we will have common exponent which is 3, right? So, how we can make this y as means in y, how we can have exponent as 3? So, for this, the next task is align the mantissas. So how we can align the mantissa? We have to see which one is having the greater one. So this will be kept as it is. X is as it is. But what we have to do with y in align mantissa? So we have to shift the mantissa of y to the right. So after shifting the mantissa, because we wanted to get 10 to the power 3, that's why we have to shift this right in y. So after shifting, we will get 0.082 into 10 to the power 3. Now we have both the exponents of equal size, so we can add these two, right? So after adding those two mantissas, we will get this 1.0324. So this was our next task, to add the mantissa. But now what is the fourth task? We have to normalize our result. So after this, how to normalize the result? By shifting the mantissa once to the right, and if we are shifting it, we have to increment or exponents. So in this, we will shift our mantissa to right, that is z value, so it will become 0.1324 into 10 to the power 4. So this will be your final result. So this, we wanted to create a arithmetic pipelining, but right now we cannot see that these two operations are how they are executed in the overlap fashion. Let us see this. So whenever we have some data, then as I told you, we require to store the result, means intermediate will require registers between every segment. So first of all, we have seen our four segments in this. After deciding four segments, now we need to use registers in between each segment to store temporary results or partial results. So we have exponents and we have mantissas. Then first one was compare the exponent by subtraction. Why we needed to compare? Because the first step of this pipelining was compare the exponents. So how we can compare? By subtraction only. So subtract the exponents. Now based on the difference, align mantissa. Then, so this portion will show us what we need to do with mantissa. This portion will show us, the left portion will show us what we need to do with exponents. Then we will require again the in between registers to store our result. Then in segment 2, what was our main target? To align the mantissa. So first of all we have to choose the exponent. So in left hand side you can see there is choose exponent, and in the right hand side you have align mantissa. So you need to align your mantissa. Then again you need to temporary result is to be stored in R. Then the next third step was add or subtract the mantissas, again storing the result, temporary result in the register. So this was segment 3. After addition we have seen we need to normalize the result. So to normalize the result again we also have to adjust the exponent. So exponent will also come into picture in segment 4. So adjust exponent and normalize result. So this way we will get your final result in this pipelining. So in today's lecture we have seen parallel processing, where we have seen simultaneous operations to be performed. Then this was the example, as you can see in this figure, where we are having multiple functional units. Then next one we have seen the classification by Flyens based on instruction and data. So instruction stream and data stream based classification, wherein we have seen von Neumann systems comes into this category SISD, and we can incorporate parallelism through multiple functional units or using pipelining. Then we have seen SIMD, means shared memory will be there, multiple processing units and data will be shared. Then we have MISD was also there, which was just theoretical concept, and the last one is MIMD, which was based on multiprocessor systems. Then we have seen pipelining. In pipelining, our goal is to divide any operation into sub operations or tasks. After dividing, we want to perform whatever sub operations in overlapped fashion. And then whichever task we need to perform, in general pipelining system will require registers in between to store the results. So we have seen this example of pipelining system, wherein we wanted to perform AI into BI plus CI. We have also seen how it is completed till 9th time, because operations, we have divided our task into subtasks, and then those operations or sub operations will be performed in overlap manner, right? Then we have seen space time diagram, which is based on segment and clock cycle time. Then we have seen how we calculate, first of all you should understand how we get this formula, which is k plus n minus 1 in case of pipelining. How we are achieving that? Because first task was completed till k, and then after every remaining task will get complete by the each, after that clock cycle, in each clock cycle, each next clock cycle, you will have one more task which is to be completed. Like once the pipe gets full, then the next cycle, next task will get complete. So this is the way. Now another thing we have seen was speed up, which is non-pipelining divided by pipelining. So we know that NTN will be the time which is for non-pipelining, and k plus n minus 1 into TP will be for pipelining, and that is how we calculate or speed up. We have also seen special cases over here. Then we have considered one type of pipelining, which is arithmetic pipelining. In next lecture you will study instruction pipelining. Then in arithmetic pipelining we have considered the how we can achieve pipelining for floating point addition subtraction. So we wanted to first of all, for constructing pipelining you should have segments. So we had 4 segments in this. One of the segment is compare the exponent, align mantissa, add mantissa, and normalize the result. Then you should be able to construct this thing. For exponent and mantissa we can have separate, we can write them in separate manner. So segment 1, segment 2, segment 3 and segment 4, how they are affecting exponents and mantissas, that we can see from this diagram. So that is it for today's lecture. Now in next lecture you are going to see instruction pipelining.